So, the outline of the talk is we're already deep into the introduction, and then I'm just going to have a brief wander through what I've been my experience of machine learning in minerals exploration. And then we're going to look at the question, as we've already learned, is that you have to start with asking the question. And the question that I've asked is, can we predict gold from geophysics? And we'll try to cast it first as a supervised learning problem and then as an unsupervised learning problem. And we'll see some results, and from that we'll draw some conclusions about what I've learned from minerals exploration. And in those conclusions there'll be sort of a number of hacks and advice and experiences that I have gained over the years. So let's start with machine learning in minerals exploration. And if you sort of plot a timeline, I'd say that the 1990s were probably what I call the early years. It was a time when, in 1992, MATLAB's Neural Network Toolbox version 1.0 came out. And that's probably the commercial package that's had the most impact on the use of machine learning and neural networks in minerals exploration. A lot of people in the early days were beholden to that package. There were a lot of academic activities during those years, myself included. I was a grad student, and I did a minor in computer science, and I chose artificial intelligence because that was a hot topic in those days. So I even published a paper on visualizing the learning algorithms of perceptrons in backpropagation. And I even learned Lisp, okay? Lisp is an artificial intelligence language, and it's probably up there with Latin in terms of the languages that I have learned and never used. But there you go. The first commercial package that I've ever seen for use of neural networks and machine learning in minerals exploration came out in the late 90s, and it was the Prospect Explorer. They called it a neural network software tool, and it came from a company called Neural Mining Solutions. And it was basically, well, they never really revealed what was in it, but it's basically you had a number of geophysical layers, and it worked out correlations between these layers, and then you could choose a special anomalous area, and it would tell you what were all the other areas that looked like it. Okay. And these guys were 20 years ahead of the time, because this is what we're doing today. Okay. They were 20 years ahead of the time, and they immediately went bankrupt. There's just no interest in that thing at the time. Then in the 2000s, I think we had the gathering of momentum. I didn't appreciate that at the time, but in February 2000, R version 1.0 was released. And about the same year, Python version 2.0 was released. Okay. At that point, you had to be a very dedicated computer science or statistics geek to be interested in R and Python. But boy, has that changed in the past 20 years or so. The earliest practical examples I saw of neural networks in minerals exploration was the work that has been done by Stephen Barnett and Peter Williams. And that was sort of in the mid-2000s. And if you guys are interested in this field at all, dig out all their papers and go through them, because these guys were really some of the key, I suppose, champions that started this area. And their focus was primarily using backpropagation neural networks for copper and gold anomaly detection. And also, I don't think we can go through this without just paying a little bit of homage to Steve Fraser, sitting down there in the back of the room, for coming up with or understanding that SOM could be used in this space as well. And we've seen plenty of some SOMs today. And I think we should mention Bruce Dixon as well, because Bruce was, as Stephen has pointed out, this definitely has been an instigator in this process. There's also another person in the room, Rob Ellis. Rob was one of the first that I knew of that sort of could see a good idea when it came his way. And so he instantly took the SOM idea and built it into a proprietary package in PHP at the date, and which was the first example I've seen of SOM for classifying the results of geophysical inversion. That was MaxSUS and density earth model, and classifying them using SOMs. And then in the 2010s, where we are now, we are seeing machine learning entering the mainstream. And so we're starting to see multiple commercial ventures being announced in this space. And in 2016, we had the Integra Gold Rush Challenge, and we had in 2017, we had the Frank Arnold's Awards. And I think that they together did a lot to sort of spread the idea of machine learning in the area of minerals exploration. And also, we now have a very mature machine learning ecosystem that exists both in R and Python. And that has meant that the development and the use of these methods are easier than ever before. But if we look at 2018, we can't escape the fact that, well, where are we on the Gartner's hype cycle for emerging technologies? Okay. If we look the hype cycle for emerging technologies, it starts with innovation trigger. We have the peak of inflated expectations. We have the trough of illusionment, the slope of enlightenment, and then the plateau of productivity. And down there in the innovation trigger, we have smart dust and deep reinforcement learning and what have you. But at the very peak of inflated expectations, we find machine learning. Okay. So a bit of reality check is sometimes not a bad thing. But machine learning is sitting up there. And it doesn't take much to go through the news, and you see things like Airtree and Blackbird Ventures. They back an AI mining exploration platform that's from the field review last year. It's a local group here in Sydney that received funding for an online AI mining platform. We have, as we saw today, Goldcorp and IBM that wants to hunt for exploration targets at Red Lake. And where, the subtitle is that IBM Watson supercomputer will learn to think like a geologist. And it's like, it is just so tempting. It's like, I could say so much about that, but I'm not going to. Okay, we're just gonna let sleeping dogs lie, I think. There's another group of participants in the Goldcorp in the challenge. This is Goldspot, and they claim that they have speared the unicorn. So there's plenty of hype down there. But I'd say a lot of the more serious work that's come out of and applied work has come out, but first of all from Integra Gold's Gold Rush. I mean, who doesn't want to crunch data and strike it rich? And there was a cool $1 million up for grabs, and more power to the winners. Likewise, for the Frank Arnold Award, that was an excellent idea to come up with, and to especially to I suppose divide it into a commercial part and divide it into a student part, and also ensure that collaboration was one of the prime requirements for these challenges. So in 2010s, we have a very mature machine learning and an AI ecosystem that's available just for grabs, for free, in R and in Python. Here's just one of many machine learning libraries in Python. This is the scikit-learn. And there are so many algorithms that you need an algorithm cheat sheet in order to walk your way through and find out which one is most appropriate for your problem at hand. So never before has it been so easy to apply various machine learning algorithms and to use them in a unified programming language, whether it's R or whether it's Python. But as I see it, in order to be effective in this space, there are sort of three things that needs to come together. You need to have math and statistical knowledge. You need to understand what are these routines doing. Likewise, you need to have domain knowledge. If you don't understand minerals exploration, you're not truly going to appreciate the problems that we're trying to solve. And because of the nature of the beast, you got to have some hacking skills. You got to be able to make computers roll over and do things in order to solve this. And if you just know math, statistical knowledge, and hacking skills, then what you're doing is pure machine learning. And I find that if you just have the math and the statistical knowledge and you know minerals exploration, well, then you're just doing traditional research like we've been doing since forever. And if you know a bit of minerals exploration, if you know a little bit of hacking, then you're in the danger zone. Okay. So it's only if you know the three things fairly well that you're actually in there doing data science. So, but having said that, let's have a look at two data science or two machine learning techniques, and we're going to have a look at a gold prediction example. So the gold prediction example we're going to look at, we're going to cast it as first as a supervised learning, and here's a whole sort of, I suppose, a diagram of what machine learning is for some people. And it's supervised learning, it's unsupervised learning, and they also put reinforcement learning, which is really just learning in real time. It's for robotics, where you quickly have to learn to update as things get thrown at you. But we're going to look at supervised learning, and within supervised learning, we're going to look at regression. So before I actually get to the gold prediction problem, I just want to use an example, a very simple and actually very difficult example that comes from Kaggle. You guys know Kaggle? Yeah, most of you do. It's a website, or it's an organization that basically provides data and problems for machine learning. So they have all kinds of problems on there, and the data is there as well. And they have these competitions where you can send in your results, and you can try to become number one, and win the coolness factor that comes with having won a Kaggle competition. So the one we're looking at here is dogs versus cats. It's actually over by now, but still the data is still there. And it's what we call a binary classifier. Okay, there's a training set of 12,500 pictures of dogs. Okay, and there's also 12,500 pictures of cats. Okay, and the problem is that you need to come up with an algorithm that can distinguish between dogs and cats. And human beings are very, very good at this. Okay, computers, it turns out, are not so good. How would you do it, Joe? What most people do these days when they want to try to solve that kind of problem is that use what's called the convolution network. So you basically you feed part of the picture into a multi-layer neural network. The first part of it will have an element of convolution, trying to find other texture or edges or something in the picture. And then you'll have what's called a polling, where you're basically trying to subsample the data. And then you might do some more convolution on it, and only finally will you get to sort of a fully connected neural network in the classic sense that's trying to sort of classify or remember the essence of these pictures, of the deconstructed pictures that are coming into it. In this case here, this is actually, I just pulled this off an article. So this is an expanded one. It's an algorithm, or it's a network that's supposed to learn in a picture to recognize cats, dogs, boats, and birds. Okay, just to make it a little harder. But the problem that we're looking at is just cats and dogs. Apart from the two training data sets, or the training data sets that has equal amounts of cats and dogs, there's also a test data set. And the test data set consists of cats and dog pictures that should not be used for the training. Okay, they should be used for after you've trained the network on the training data. You can then run the test through and see how well does your network perform, or your algorithm, or whatever you've done. How well does it perform on things that it hasn't seen before? If it performs well, if it's very good at classifying cats or dogs on pictures that it's never seen before, then you have a good classifier. Okay, it's generalized the learning. It's learned something about the cattiness in the picture or the dogginess in the picture, and not just memorized 12,500 dog pictures and 12,500 cat pictures. So we want to have a trained classifier that if you give it a picture of a dog, it just spits out that's a dog. Now, state-of-the-art computer vision classifiers, they can get better at 80% accuracy of this. Okay, so out of all those pictures there, they can get better than 80% right. Okay, because the nature of this test is that, you know, you're going to see equal amounts of cat pictures and equal amounts of dog pictures. So you might just come up with a strategy that says, I'm just going to guess randomly. Okay? And if you guess randomly, you're going to be right 50% of the time, because half of the pictures are cats and half of the pictures are dogs. Okay? That's a bit like going to Crown Casino and just betting on red all the time on the roulette. Okay? So random guessing will get you 50% accuracy, and you want to do better than that. Now, we can cast a goal prediction example as something like that. We'll have a training set where we have multi-dimensional information, and it might be geology, it might be geophysics, it might be geochemistry, and they will be labeled not gold, or they will be labeled gold. Okay, so we have some examples of the geophysics, the geochemistry, the geology in areas where there's gold, the geophysics, the geochemistry, and geology in an area where there's not gold. Likewise, you'll have a test set that says not gold and gold, and we can then run those test sets through our trained gold classifier, and we'll see whether we get gold or not gold. So the idea is that we're going to try to predict if there's gold somewhere based on regional or local geophysics, geochemistry, and geology data sets. Now, that is a lot harder than recognizing cats and dogs. Okay. First of all, it's harder because dogs versus cats, that's actually easier than not cat versus cat. Okay? Secondly, it turns out that the number of positive examples that we have, the number of gold mines out there, is small. Okay, so we have an unbalanced trading data set. And then finally, you know, because we're dealing with geological, geophysical, and geochemical information, there's noise, there's error, and uncertainty in there. So this is a lot harder problem than trying to recognize cats and dogs. If you want to sort of just run with this stupid cat and dog parallel for a little longer, then you can see that, you know, there we have the dogs and there we have the cats. And that's actually a lot easier than trying to classify not cat versus cat. Because it's easier for a classifier to learn something about the characteristic of dogs than the characteristic of cats. And then whenever you show them a new picture, it can say, well, it's more of a dog than it's of a cat, and you only have to choose between two. Okay. What you're really dealing with is non-cat, okay, and then pictures of cats. So you have all the animals in the world, except for cats, on the non-cat side, and then you have the cat side there. Okay. And that's a lot harder for someone to train on. Because when you're doing the cat versus dog, what they all do is that they come up with, they try to find the differences between cats and dogs. Typically comes down to the color of the skin. Okay, cats typically have slightly different color range and furs than dogs have. It comes down to the texture of the fur. You know, cat fur just looks slightly different than dog fur and so on. Some people are saying there's a slight, most of the cats that you see there are stationary. Okay, when you take a picture of cats, they tend to sort of just to look at you arrogantly. Okay, whereas dogs will slobber, or they will run, or they will jump. Okay, so there's a different distribution to the dog pictures than there is to the cat pictures. Okay, you don't have that advantage when it's cats against the world. Okay. Another problem that we have if we want to do this gold predictor is that we have many more examples of not gold than we have of gold. Okay, otherwise gold wouldn't go for, you know, more than $1,000 an ounce. So not gold is common and gold is rare. Okay, so there are very few examples of gold, and we have many examples of not gold that are available for training. That's what's called an unbalanced data set. Okay, and it's a bad idea to go and do a classifier with an unbalanced data set. Okay, because, you know, the first thing that happens if you do something like that, if you do train a cat or a cat non-cat on this kind of data set, the algorithm will invariably come up with a rule that says it's not a cat. Okay? It'll just constantly say it's not a cat because it will be right. There's only 7% cats and there's 93% non-cats. So it'll be right 93% of the time. And it'll just say, that's pretty good enough. Why should I even bother with it anymore? Okay. So unbalanced data sets is a bad idea because you can come up with you come up with an algorithm that has 93% accuracy, And it will never identify a cat ever. Okay, and yet it's 93% accurate. That's not good. Okay, so what are the strategies that you can use for unbalanced data set? And you can either, there are many, okay, but let's take the two most simple ones. You can undersample. You can just say, well, I'm just going to throw a lot of non-cats examples away. Well, that's probably not such a cool idea, but if you have a lot of, if both of them, if they're large amounts in both areas, that's probably okay. Well, you can do the other way. You can just duplicate the other ones so that you get some oversampling and you start to get a little more of a balance. Look, there's at least 6 or 7 different other techniques that you can use to get around this. But it's just something that you need to be mindful of if you want to look for something rare in a sea of the ordinary. So with that in mind, let's go and have a look at a very simple gold prediction example that I've run on public data sets covering Victoria, my home state, and part of New South Wales. And in there, I just pulled out from the Geological Survey of Victoria their geochemistry database. Okay, and there are 66,000 or so gold geochemistry samples. Okay, and they will say, they'll give you the location and they will give you the amount of gold in ppm or ppb at that location. Okay. So that's a good thing to start with. If you break it up, then most of them are not gold. Okay, 65,700 of them are less than 1 ppm gold. Okay, so I just classify them as not gold. Okay, and then there's 800 samples in there that's more than 1 ppm gold, and I'll say, well, that's the gold. Okay, that's a pretty unbalanced data set right there. Okay, but we know how to counter that now that we realize that. On top of that, we also have the geophysics, the radiometrics, the Landsat, all these things from the geological surveys, and we can use that as well. Okay. So we're looking basically at a situation here where we have training sets. We have 65,700 of not gold, and then we have 800 sets down there, 800 data sets that are gold. Okay. So unbalanced as ever. Okay. I also made the same discovery that Matthew did, and that's you can't make it. It's a bad idea to use a predictor or to use geochemical values just in ppms. Okay, the range is too large. Okay, it goes from 0 to thousands of ppm. So what you want to do is that you want to do the log 10 value. So we're working on the log value. Okay. So the idea is basically that we take 24 layers of regional geological, geophysical, and what do we have? Remote sensing information, and we just try to put that through a trained gold classifier, and it should come out with an estimate of what is the log 10 of the gold value in that area. Sounds pretty good. So after we've done training with these 5,000 geochemistry site, then we use the trained classifier in Oracle mode on all the other data, all the other geophysical data in the state. Okay, and then we're going to get a statewide estimate of gold values. All right. So with no further ado, here's the log 10 value of gold in the state of Victoria. Okay, and you look at that, you think, oh wow, there's a hell of a lot of gold down in Melbourne, and the Victorian Alps is just chock-a-block full of it. Okay, so gee, what's going on here? Well, first of all, let's go in and look in an area where we actually have a lot of geochemistry. So we're going to zoom in just on the central Victorian goldfields. Okay, so we zoom in on the central Victoria goldfields, and here we have the superimposed. You have the gold. You have the chemical gold values marked as little dots. The hotter ones have more gold, and the bluer ones have no gold. And then underneath we have the estimated values. So you can see there's a sea of blue up here in the geochemistry. There's a sea of high here. This is what is that? This is Bendigo. This is the Bendigo area. we've got Ararat over here, and we've got I think it's Castle down there. So so the geochemistry at least matches the values. Because I'm just going to take the geochemistry off now. Oh, that's the wrong one. Sorry. So I'm going to take the geochemistry off and just go back and forth, and you can see that you get nice warm colors where you got a high geochemistry value, and you get nice low blue colors where you have lots of low geochemistry values. Okay, so at least wherever we have geochemistry, it's fitting what it should be doing. Okay, but then what about the rest of the places where we don't have any geochemistry, where it's sort of interpolating between sites? Is it doing a good job or not? Well, what we can do is we can just put on the historical gold fields in Victoria. This was an incredibly rich region that's been producing for the past 150 years. And so in dark we have sort of the very crude outline of the gold fields. And if we now put the estimated values on, you'll just go back and forth a little bit, and you can see that wherever there's a gold field, there's also a high value. Okay, so it's actually doing a pretty good job in the central gold fields.
Asbjorn, can I ask a question?
Yes.
The areas where you've got your training data, those gold samples,
yeah.
did you push those training data back through your model after you built it? Because you've got highs over where your samples are, that you trained on those samples. So did you? Those points,
yeah, exactly. That's a good question. Are the points that was used to train now here in the predictor? Have they gone back into? Yes, they have. Yes. Okay. So it's a double. It's just a validation to show that wherever the geochemistry was, at least it's predicting what the geochemistry said.
Yeah, because it's told us.
Yeah, exactly. But now we're looking at wherever there wasn't any geochemical data. Exactly. So it's not doing a bad job, at least not in the central goldfields. Okay. But yeah, so there's elevated gold predicted over most of the historical goldfields. Well, that's a relief. Okay. But what's happening in the rest of it? It turns out that a gold predictor, at least my gold predictor, is a decent interpolator, but it's a bloody poor extrapolator. Okay. A prediction will be completely unreliable over geology that's not been sampled by the geochemistry. Okay. And so what you have, for example, down here in Melbourne is that there's, this area here in Melbourne where we have all this gold. That's just because the geophysics is screwy over a large urban area. Okay. So you get geophysics that's not like what you see in an urban area, but if you're telling it that you got to use geophysics to predict gold, it'll just predict something screwy, which in this case is a high gold value. Likewise, you can see that that's actually the spatial distribution of the data that was used for training, and you can see, well, if we sort of draw a line around it and say, well, this is sort of where I'm comfortable in terms of the geology. That's where, that's the geology that's been sampled by the geochemistry. So, whereas once we get over in this area here, there's a whole different geology. It's the Victorian Alps. And so that's not been sampled by these geochemical at all. So you can't extrapolate out there. So in that area, yeah, you're doing okay. In this area, don't trust a single point of it. Okay. Having said that, the geology in central Victoria continues up undercover in the north, and it's the same geology. So it's not a bad. It might be a good predictor up in that area. Right. So just to say, if we use this as supervised learning, hey, I've constructed a gold predictor. I used 24 layers of geological, geophysical, and remote sensing, and I used supervised learning techniques. I need some funding now. Okay. Of course, the prediction is reasonable in areas where we have good teaching examples, where we have geochemistry and regional data. And the prediction, just notice how noisy it was. That's because geophysics is noisy. Okay. So it's susceptible to noise in the data. You get garbage in, you're going to get garbage out. Okay. So the more time you spend on cleaning up the data, the better. Okay. And of course, hey, I used 24s, which was rather arbitrary. I really like how people look at these techniques to determine which are the input parameters that are worth keeping and which are the ones that will just confuse the issue. And that is absolutely what you need to do there. So the question, of course, you have to ask yourself, would more data layers make the prediction better? And what would happen if we had irrelevant data? Will that make the prediction worse? But sometimes it can be very helpful to recast the problem. And you can say, well, why don't we, because there are so many algorithms out there, why don't we try to cast this as an unsupervised learning exercise? And the unsupervised learning, where we're over in this area, in this part of the machine learning space, and we're going to look both at sort of, I suppose, dimensionality reduction and clustering. Okay. Why do we want to do it? Well, sometimes it's helpful just to recast this problem to investigate other algorithms, see if they do any better. Also because, you know, there's no one miracle algorithm. Okay, there's not one that's going to be better than the other. You know, there are algorithms that have strengths and features, strengths and weaknesses, and it's up to you to find out which are the ones that work best for your problem. So, I'm going to recast this problem as a sum problem. Oh God, not another sum, but there we go. Okay, so the idea is basically we're just going to take these 24 layers of regional geophysics, and we're just going to classify them. Okay, we're just going to run them through a sum, and then we're going to classify them into, I think, I did 16 different classes. And then afterwards, we're going to have a look at where do the 800 samples that are gold, what classes do they hit in the sum? Okay, and then we're going to see those classes we're going to use as a predictor for gold. So some basically inputs down here below, and there are 24 layers, so there's 24 input channels. We do this by points. Okay, we're going to put all the 24 regional grid points through, so there's about 500,000 training points, and they each have 24 dimensions, and we're just going to put them through a sum, and we're going to cluster them into 16 classes. Okay. After we've trained that and done that, we're just going to pump through the locations where we had the high gold values. Okay? Those 800 locations, we're going to pump those through and see where they fall in the sum class, in the sum classifier. And here are the 16 4x4 nodes of the sum. Okay, and I pumped 801 gold sites through the geophysics and the geology and the remote sensing data through there, and we can see that they all sit up here. Okay, and they hardly don't touch these classes at all. Okay, so you say, well, those 4 classes are the one that's interesting. Okay, so if I look at the entire state, okay, this is a sum map that I have, and that's a 16 class sum, and it looks, as they all do when you do these things, surprisingly like a geology map. Now again, let's just try to zoom in on central Victoria. Okay, so here's the sum, and each color is a different class. Okay, and if I first of all overlay the known gold fields, we can see that all the gold fields sort of fall within pretty much the class 3, which is the orange class, which is the one that had a lot of gold hits. Okay. So we can sort of say that, right, okay, well, orange, if you want to explore for gold in the central part of Victoria, that's the area you want to be. Okay. And of course you can do that statewide. You can just isolate class 3 and you'd have a prospectivity map for gold akin to, or for geology akin to central Victoria. So, by using sum, we've effectively sort of reduced the dimensionality from 24 down to 1, and we've made a prospectivity map. What I like about sum is that, as opposed to the regressor that you saw earlier, is that this is rarely insensitive to noise in the input data. If you have sufficiently small number of classes, then things tend not to oscillate too much in and out of classes, and so you get things that are relatively coherent. And it's already been pointed out by Stephen Fraser is that, you know, I'm lucky enough that I have data that completes coverage, but this can work just as easily with incomplete coverage, which is a very powerful feature that the regressors don't do. So in terms of conclusions of what the hell have I learned from machine learning over the past 20 years is that, don't believe in one miracle algorithm. It was so that, 10 years ago, it was so hard to code up an algorithm that you would code up an algorithm and that would be the one that you would be selling to the market, or that you would be selling at conferences, or that you would writing papers about. Okay. But nowadays, it is so easy to change horse midstream. Just go and try another algorithm. So don't believe that there is one miracle algorithm that will do this. Second, so try different approaches, because they all have strengths and weaknesses. Yeah, okay, here comes a couple of hacks for you. These are mistakes that I have done in my past. Okay, and the first one is always normalize your data. Okay, this is Matt from Tasmania had exactly the same problem. Okay, you have to normalize your data. You can do, you can squeeze it in just from 0 to 1, and you can do a zero norm. I like this zero norm personally, but you got to normalize it. And then here's another trap. Okay, once you've decided on a normalizer, okay, you got to save that one, and all the new data that comes in, you have to normalize in the same fashion. Okay, otherwise you get garbage. Okay, it's garbage in, garbage out. Okay. So keep track of your normalization. Be sure that everything, also the new data, is normalized in the same fashion. Okay. Garbage in, garbage out. You have to understand your data. These routines will take anything and they will come out with a number for you. Okay, and it can be so hard to recognize that it's garbage. And so to avoid that embarrassing situation, be sure that your input data isn't garbage, okay? So exploratory data analysis, that's just mandatory. You guys you have to look through as many dimensions and look for outliers and do all the preparatory work. This is just me. I really like that I can get all this data for free from the geological surveys. I mean, God bless them, and God bless Australia for this great country we live in, okay? But the state of publicly available geochemistry databases is appalling. Okay, it's like they're full of, half of it's in ppm, half of it's in ppb. You got repeat measurements in there. You got points that are wrongly located. You have points from other states that have found their way in there. Okay. And then don't get me started about, as you said, the different provenance of this geochemical data and the accuracy that's involved, or the lack of accuracy that's involved in there. So you're gonna, and you always get a SQL database, okay, or a Microsoft Access database, and they're so as quickly as possible. If you're in Python, if you're a Python person, get it into a data frame as quickly as possible, because they're your friends. With those it's amazing how quickly you can sort of weed out these problems, identify them, and get them sorted out. So I get to know your data frames, because they will save you many times. Okay. Yes. No one ever really shows this because it's so boring. But you have to look at your performance statistics. Okay, when you're training your networks, and when you're doing supervised training, or when you have classified training, you have to look at how well is your database, how well is your classifier performing. Okay, and there are all kinds of measures, from precision, recall, confusion matrix, Cohen's kappa, your ROC curves. They're all relatively simple mathematical constructs to get your head around, and they will save you time and time again. Okay, it's I don't think you'll have much luck actually convincing your clients that they're worth looking at, but you will sleep a lot better at night if you've been through these before you hand over a product. The machine learning is the fun part, but it's also the easy part. Okay, it's like what comes afterwards. That's the hard part. It's understanding and communicating the results that come out of these classifiers. That's paramount. So you really have to understand what is it that comes out, and how can it best be used by yourself or by your clients. And then I have to say that all these algorithms here, they work on the fact that things are correlated to one another. There is some causation between the geophysical data measured from an airplane that flies at 200 kilometers an hour, and then, the value of gold in a small soil sample, okay, down below. But it's a tenuous one, okay. It's one we have established. There's a relationship between the two. But it's not always that correlation is the same as causation. And sometimes it is, but you don't even want it, okay. I saw people at Exploration 17 that discovered that, if you try to classify, gold geochemistry and the DEM, okay, they found that there was this fantastic correlation between high gold values and deep hole in the ground, okay? All right, and sure enough, there's a great correlation between mines and high gold values, but that's not really what you're looking for, okay? So you gotta be careful with these things. And so references credit has to be due where it's due. And with that, I just want to say thank you. I think it's an exciting time we live in. This is, I'm not trying to do a Malcolm Turnbull here, but this really is interesting. Never before has machine learning been so, I suppose, readily accessible. Never before have we had so much glorious data to wallow in, and never before has so many people been interested in it. So these are good times. Thanks very much.
Any questions for Asbjorn? Dave?
Yeah, Asbjorn, very good. I think it was a nice way to finish off. I have a philosophical question about normalisation.
Philosophical one,
Yeah, well, you're on the philosophical.
Yeah, no, I'm a practical guy, yeah.
So, normalisation of data.
Yeah.
And we've seen magnetics presented as part of a song set and a learning curve.
Yeah.
Now, if you think geologically about magnetics, a 1 nanotesla anomaly could be just as important as a 10,000 nanotesla anomaly.
Yes, yeah.
Now, if you translate that back to susceptibility, where we'd all like to be, in
Yeah.
the SOM layer,
Yeah.
when we normalise that, what do you think the impact is of the 1 nanotesla anomaly that we would still like to be able to see?
Well, if you do it so that you get to a standard deviation of 1, that's sort of like doing I think it's the same as doing an equal area, like a histogram normalization. So in that sense, you're going to get a bit more weight to the smaller values.
That's assuming the 1 nanotesla is going bottom.
Yes, yeah.
If we've got susceptibility, we have actually got a better chance of pulling that out.
That's true. Yes. Yeah. No, that's true. And again, people were talking about, why don't we use the inversion results instead? Why, instead of just looking at this, just the raw geophysical observations, why don't we look at something that has a bit more of a geological and physical relevance that sort of takes out the depth dependence and all that, and actually assigns depth values to it. And I'm all for it, but I just don't have supercomputers to run the state of Victoria.
Do you think it's like building a model on the back of another model that's got error and inaccuracy? Like the data is the data, and it's like it's measuring a physical property that is there.
Yeah.
And an inversion is completely dependent on the package I use, the parameters I choose, X, Y, Z. So it feels like using an inversion as input for this type of thing is just adding on a layer of uncertainty to your model, if you know what I mean. Like,
yeah, I know that. I've seen very good examples with inversion results being used in at least in some world, both from Steve and from past experience with Rob Ellis. So I'm not one for discounting that, but also if you're a quick and dirty guy like I am most time, then you don't.
So
Stephen was saying something. Yeah.
Of your petrophysical properties in your inverted model are relative, because then when you do the fusion, to do the song, you really start to look at gradients, and the gradients really are invariant. I mean, they might be out like that, but you're still going to get sort of edges within your model.
Sure. Aren't there edges in the data also? Like there's no new information that you're getting from the inversion that's not contained in the data itself. You just expressing the data.
Geophysical data.
Yeah.
Well, I think there's massive amounts more information in the inversion. Because because you've actually got a model that can be continued up to actually produce that data set. It might not be unique, or it can be unique, or ideally it be unique, but the reality is that so long as it's relative, I think it's quite meaningful.
Oh, no, I agree it can be meaningful. It seems like anyway. This is probably a conversation after.
As I think Dave was talking about, I spent the first couple of years of as a pebble puppy running around out of a helicopter bump hunting in Western Australia looking at kimberlites, and it was virtually soul-destroying. But the reality is that they were up to 2 or 3 nanotesla dipoles.
I see about the word unconstrained inversion sort of is already ringing up alarm bells when it has the word unconstrained in it. And those constraints are based on the algorithm that you decide to select and various other things that are just model specific. They're not, it's not data, it's a model.
A mag reading is 50 metres off the ground is sampling hundreds of metres around. So you
The wavelength of that, that information about where you're cramming your mag sus measurement in the inversion is related to the wavelength of the measurement. How does the inversion know where to put it if that information is not?
It uses all the mag readings in the data set to sort of generate the separability model.
It takes this one, but it also takes the next one along the flight line, and the previous ones are the ones in the adjacent flight line. So it's a combination of all that.
It will be much more compact than your
GeoPhysics, for instance, like to make you a compact source down up high, or would you like a big one down deep, or would you like a smoothly varying model, or would you like a sharp edge model?
I like a constrained model.
Yeah, I like a constrained model, yes.
Brendan, I think where it comes unstuck for some people is that the way that I've seen this done a few times, which makes me a bit cautious, is what they've done with the UBC inversion. They've stuffed around with the depth weighting crap because they're saying the sources are deep, so we're just going to shunt everything up into the top layers so that we can get a sort of superficial bedrock geology. And that's sort of, it's that thing that makes me a bit nervous, because now someone heavily artificially bumped that inversion to the top
But if it's not constrained, then how do you know how sharp the gradients, how harshly to push the model up? If it's constrained inversion, I completely agree. If it's unconstrained, it seems.
I think it's the other way though. If you've got poor geochemistry and you try to compare that to an airborne signal, that's miles out. I think by doing the inversion, you're going to be just that little bit closer. It's comparing a point sample to a potential field.
Yeah, I'd be sort of.
The wall speaks. The wall speaks.
I had a question actually, and it's something I've come up with on a smaller scale. So the idea of it being a terrible extrapolator, and I found the same thing, but the one issue there is that you can say, okay, so now we're in the Australian Alps and it's all rubbish over here, but so when you do the same thing, but you don't always know that you've done it, so you're looking for a warning sign, say, have I just come up with extrapolated rubbish over here? Sometimes it's really obvious because you have some sort of constraint or geology that tells you that. Other times you've just potentially crossed into a new domain, predicted absolute garbage, but you have no idea that you've done it whatsoever. So do you have any thoughts on that, sort of warning signs to say that, oh, I've actually exited the domain where this is relevant, without actually having any other constraints to tell you that you've done? Is there something that comes out of it that can actually warn you that you've made that error?
Well, I think you could do something akin to, like in Victoria. Okay, there's 65,000 locations where I have geochemistry, and like at least in a sum approach, I can work out what are the cells that's been hit by these 65. What are the classes that have been hit by these? Okay, and then I can go out and I can put the geophysics through the sum, and I can say that whenever I'm getting away from classes that haven't been hit by the geochemistry, then I'm in danger territory, and I can even give an estimate of the danger by the distance that I am from the geochemically populated classes to where I just happen to be at that point in time. What would you say, Steve?
I'm just going to comment basically on your classes.
Yeah.
You're really doing you're really just displaying the BMU colours, aren't you? The best matching mineral, the covectors.
No, not in there. I'm displaying the hits. So So it's not. I'm not showing the BMUs. I'm not showing the U matrix. No. Yeah, I'm just showing the hit matrix there. So I put in when the slide you're referring to is where are we? How can I do this? Here. Slide we're referring to. Oops, there. Okay. So it's just a heat map. There's 800 geophysical points in my entire data set that has gold associated with it. And I've just fed those to the geophysics of those 800 points through my sum, and I'm just counting how many hits do I get in the different classes. Okay, yeah.
All right, well, thanks again, Asbjorn. That was good.
Yeah.
I think my name is down for the last block, but really it's about you folks. And you've got some questions or comments, and I'd particularly like to hear from some of the non-geeks that are not in that space right now, and just share your thoughts as to how the day. I don't think you're doing AI currently, right? Yeah. Just what do you see as potential for something like this? Would you, for me, because I'm not in the space, I'd say I'm probably going to find myself a good service bureau, somebody like this gentleman or something, and say, take a problem to somebody who's spent time figuring it out, because there's just too many rabbit holes for me, but that's, lazy. Anybody else want to comment? Or? Well, EJ, you're sort of in that alternate space in a larger sense. What do you, you track it, when is it going to mature to the point where real exploration problems can be solved and it becomes mainstream?
Well, I think people are looking at, a lot of people in prospective mapping is looking at how to integrate data sets and doing the machine learning and come up with a final map for targets, for example. But I think my experience of teaching kind of unit that I'm doing at the moment for my master's students is that it's that just mineral systems or the mineralization that model, the geological model, is the one that drives success for the target, not the integration methods. So we've got to get this perspective on what is the value of machine learning for exploration targeting, right? I think the real value is how machine learning can be integrated in analyzing the mineralization processes that defines the model, right? And for example, I think the Watson, the geological document analysis, and our group is also working on that with the geological survey as well, that, just analyzing what people has written and to see what is the knowledge about the mineralization associations with the different rock types and alterations and mineralization, and when is the geological era this occurred, this kind of information has to be all extracted and validated before you put it into this model. I think that is the future for mineral exploration. That's my view. In terms of what methodologies you apply, as you mentioned, just whenever we do any machine learning project, we try different methodologies, and they all kind of come up with a similar results. So it's not the integration methods, and that's widely available. It's what you put it in, and as you said, the input, garbage in, garbage out. So the feature selection process is the one that, if you go just machine learning mode, you can just keep trying, like the student who's doing the embedding analysis on element geochem, and using a random forest to select features like many of you guys did here, and then you do the visualization into the space where you're looking at. So you can use machine learning in different aspects, but I think what you have to really focus is the knowledge discovery part.
It was 4 years ago, John Horonsky asked me to put together a paper for Econ Geology meeting in Keystone, and he asked me to put about geophysical signatures of mineral systems, and there really wasn't much out there, so I sort of spitballed it and said, well, I grew up in the generation of people that focused on targets. We characterized this usually very anomalous aspects of geophysics in particular, that we'd describe a target, you know, the VMS or a porphyry copper or magmatic nickel. And I said that it's the old story about, you know, you've probably heard it, the one about the gentleman looking for his key outside the pub at night, right? The one where, how many of you heard this story? It's a good story. Anyways, the local constable is coming down the street around 11:30, is just after the pub is closed, and there's this gentleman standing underneath a street lamp, obviously in distress, obviously had a fair, you know, a few pints. And the constable says, "Sir, what are you doing?" He says, "I lost my key." And he says, "Where'd you lose your key?" And the man points off into the dark. And he says, "Why are you looking here?" "Because the light's here."
Can't see.
We all look where there's information that we can recognize and we're comfortable with. Last year, Craig Hart, who runs the MDRU shop, was talking about background responses as sort of the footprints out from mineral systems. And he says, as far as he was concerned, you get very far away from an actual deposit, and there's all just sort of geological noise. It's very quickly, the concept that you would have some sort of multi-kilometer footprint like in an oil system, he says, in minerals is probably, for him, he's never been able to see it. But what I asked then, maybe the greatest role for AI will not be in the targets, but explaining the environments that these deposits sit within. Because we have a huge amount of data. We just don't collect it over known deposits. We collect it everywhere. But we always say, well, I'm here, just like your story. Where are the things that high-value targets that I want to follow up? But if we truly believe the paradigm that these things have some sort of larger extensional geochemical characteristics or geophysical characteristics, how in God's green earth are we going to ever find them with the normal approaches we have? Because we don't have the ability to pull out that background information very effectively. But AI might be able to do it because it doesn't care. It doesn't care if it seems like a wasted effort. We judge our time as being valuable, but a machine program doesn't care. So to me, maybe the support it's going to provide us is the ability to meander through large amounts of information. And like, I understand the best paper award, my colleague Daniel Sotel yesterday, was all about the data we normally throw away, right? The stuff that most people don't look at actually contains information. We just don't normally look in that box. And I think AI could just, you know, potentially all these computers like SETI, you could just sort of set it aside and thousands or millions of computers could look through. You don't need a cloud and, you know, Dave's big billion-dollar system. And just look for information that we could say, these are the patterns these things might actually produce when we're collecting all this information. So that's my shot on that. Anybody? Kim?
In terms of the mechanics of it, how do you sample the geophysical data set at the geochemical points? Are you just taking a point reading, or are you taking a buffer with an average, a median, or a max min, or something?
No, I was pretty crude. I just did a sample on the grid. Yeah.
Right.
Yeah.
Yeah, I'm just wondering.
And the grid cells, the geophysical grid cells are 500 meters. They're big. So yeah, there are cases where you have 2 or 3 geochemical observations within the same grid cells, and they will all get the same information. So you'll have conflicting information.
And that was just the state data. You didn't do any massaging to that.
No.
Yeah.
No, this was just it's more.
I guess
more,
the other thing
yeah.
is that the danger of using RTP, of course, is in areas of remnants that the RTP is going to be distorted.
Mm-hmm.
And I would have thought that deposits would be more likely to be on boundaries, so a horizontal derivative is probably more relevant than a vertical derivative.
Yeah, when I say geophysics, there's potential fields and there's various derivatives of the potential fields. Yes, to allow the algorithms to sort of capitalize on those very features. Yes.
I think we can call it a wrap, folks. I'm happy with that. Thank you very much.
Okay.
Thank you.
All our speakers.